All right, so I hope everyone's enjoying the snow. I sure am, except that my snowblower didn't work this morning. So got a little extra exercise, which isn't a bad thing. But all right, so hopefully this will just be a Tuesday event where we don't have classes in person. Hopefully Thursday we'll be back to normal. I don't see any reason why that won't be the case. All right, let me share my iPad. All right, so if you remember last time, there we go. So we were talking about iterative methods, so specifically Jacobi, Gauss-Seidel, and SOR. And that was in juxtaposition or contrast to direct methods such as Gauss elimination, LU decomposition. We also discussed the Thomas algorithm for Dynamical Systems. So the whole point of iterative methods was they are generally more effective and efficient for very large systems of equations, and they also are very easy to implement on a computer. So the algorithm, the iteration algorithm is very simple, and you just repeat it over and over and over and over and over again until it converges iteratively to the correct solution. We have one last topic we want to discuss in systems of linear algebraic equations. That's eigenvalues and eigenvectors. You've heard me mention these a couple times already throughout the semester, so we need to kind of solidify that a bit. So the two places where we've mentioned eigenvalues of a matrix is the condition number. Remember, the condition number had to do with estimating round-off errors in, for example, doing the inverse of a matrix or Gauss elimination. So we could estimate the effect of round-off errors on that process using the condition number. The other place where we saw it last class was in terms of the convergence criteria. So how we know that the iterative process is going to converge to the correct solution. And we said that you can prove mathematically that the eigenvalues of the iteration matrix all have to be less than 1. Now, more interestingly to us, there's also a lot of physical contexts in which eigenvalues as well as eigenvectors play a prominent role. So I want to discuss those a little bit today to make it clear to us why we care about eigenvalue, eigenvector problems. It's not just because mathematicians love them, although they do. It's also because we as engineers run into these all the time. So the two big ones that I'm going to discuss today are in solid and fluid mechanics, where the principal stresses and the principal axes on which those principal stresses act, those are based on eigenvalue, eigenvector problems. Likewise, principal moments of inertia are also based on eigenvalue, eigenvector problems. So if you've had 202 or if you're taking 202 now, this is something that you have seen or will see is stress tensors and getting principal stresses and principal axes from those stress tensors. So I'll derive that quickly in a little bit just to show you where the eigenvalue, eigenvector problem comes from, as well as, again, principal moments of inertia. The other big application that's very, very common in engineering is in dynamical systems. And a dynamical system is any system that's changing with time. So it is a biological system, a chemical system, an electrical system, a mechanical system, where things are changing with time. It's usually governed by ordinary or partial differential equations. And we like to solve them, analyze them, learn all kinds of things about those dynamical systems. Well, one thing that we often care about is what are the natural frequencies of vibration of such a system. So, we've all seen the opera singer singing at just the right pitch so that frequency incites a natural frequency in a glass that then shatters. Or if you've seen the Tacoma Narrows bridge collapse from the early 1940s, there's a great video of that. So if you haven't seen that, definitely look it up, Tacoma Narrows bridge collapse. And that was a case where a resonant frequency was incited by the wind passing by the bridge structure. And so it incited a natural frequency, which then caused large amplitude vibrations and eventually a collapse. So natural frequency of vibrations is a very prominent, very important example for us as engineers. Likewise, stability of these systems also turns out to be an Eigen problem. So the idea in a stability context is, if I just give a small little perturbation, like a wind blowing across a bridge deck, and what happens to those small disturbances? Do they stay small? Do they decay? If a gust of wind comes, do those little disturbances decay out, or do they grow? And if they grow, then the system is unstable and the bridge could collapse, the plane could crash, or whatever the context is. So all of these things, all four of these are eigenvalue, eigenvector problems. I'm going to look at these two, principal stresses and axes, and natural frequencies, as two examples. So we're going to ask a physical question. In each case, we're going to ask a physical question, and it'll turn out that asking that physical question requires us to answer a mathematical problem, which is the eigenvalue, eigenvector problem. Where you'll see these dynamical systems problems, this is in MMAE 305. So you'll see those there. All right, so let's talk about some mathematical considerations first, how we define and get these eigenvalues and eigenvectors, and then we'll look at those two specific applications from our physical engineering context. So let's say we have a square matrix A, it's n by n, and this is the so-called Eigen problem. AU is equal to lambda U. So this is similar, but a little bit different than our system of linear algebraic equations, which was AU is equal to B. So in that sense, we had an A coefficient matrix, which was known, a U solution vector, which we were looking for, and a right-hand side vector B, which was also known. Now, the only thing that we have that's known is our square matrix A, and we're looking for the lambdas, which will be the eigenvalues, and the corresponding U vectors, which are the eigenvectors, that satisfy this relationship. Now, I'll give you a very clear geometric interpretation of this on the next slide, so that'll be very obvious. And we'll contrast it to the AU equals B situation. But right now, let's just kind of define our terms. So again, A is the only thing that's known. Lambda is an unknown scalar. It usually has some physical meaning, has something to do with the principal stresses. It has something to do with the natural frequencies, as we'll see. So it's a parameter that has some physical meaning. The U sub n's, those are unknown vectors, and those will be the eigenvectors. Again, they usually have some physical context, some physical meaning within the context of a particular problem. Now, if I just look at this equation and I have my A matrix times a vector U is equal to some scalar times that same vector U. So you think for a given A, it's probably not very often the case that I'll have a lambda value for which when I multiply A times the U, I really get back the same U. All I've done is made it shorter or longer based on the size of lambda. So for most values of lambda, for the vast majority of values of lambda, the solution vector U is just zero. It's the trivial solution. So in most cases, for most values of lambda, there is no solution to the system of equations. And so we don't have an eigenvalue and eigenvector. But so what we're interested in are those few special values of lambda that do give us non-trivial solutions. And as I've said before, non-trivial, trivial, that's just fancy mathematical talk for equal to zero. So a trivial solution is equal to zero, non-trivial solution is not equal to zero. So the eigenvalues are those values of lambda that give us a non-trivial solution to this equation. And again, they're special. There's not very many of them. In fact, there's only capital N of them, given by the size of the matrix A. So there's not very many of them, and they're special in the sense that they have this interesting property where when you multiply A times U, you get back U, but just scaled longer or shorter. So a vector pointing in the same direction, just scaled longer or shorter based on the value of lambda. Those u's then are the eigenvectors. So for each lambda, there's a corresponding u. Okay, so that's the basic idea. Now, as I said, there's a graphical interpretation of this, which I just hinted at a moment ago. If I have any vector matrix A, and I multiply it by a vector, what that does is it does some sort of transformation on the vector. So for a given A and I multiply that by a vector, it might translate the vector in the coordinate system, it might rotate it, it might stretch it, make it longer or shorter, or some combination of those operations. So A times U does some sort of transformation, graphical transformation on that particular vector. So if A times U is equal to lambda times U, then what that means is that particular transformation is a very special one. And so if I had originally a vector U, like so, and if I multiply by A, if U is an eigenvector, so I'll call it U sub n, if that is an eigenvector, then when I multiply by A, it gives me the same vector back pointing in the same direction, and it just makes it longer or shorter. So it's now lambda n times U n. And so again, that's very unusual. It's very special. For any A matrix, there will only be capital N such values of lambda and corresponding eigenvectors U. So how do we get the lambdas and the U's? Well, we start with the system that our Eigen problem, AU equals lambda U. And I insert this I here on the right-hand side. Remember, I is like multiplying by 1, so it doesn't change anything. But what it does is it makes the shape of the right-hand side the same as the shape on the left-hand side. On the left-hand side, I have an n by n matrix times an n by 1 vector. And now I have an n by n matrix times an n by 1 vector. So it makes the shapes the same. And that is so that I can bring this term over to the left-hand side, factor out the un, and I get a new coefficient matrix, A minus lambda times I. That's my new coefficient matrix, which is n by n, times the vector un is equal to 0. Notice that's a bold 0, so that's a 0 vector. So all I've done is rewrite the Eigen problem in the form of a system of linear algebraic equations, but you'll notice the right-hand side is 0. So we call that a homogeneous equation because the B, the right-hand side, is 0. So we have a coefficient matrix, A minus lambda I, times the solution vector we're looking for is equal to the right-hand side vector, which in this case is now 0. So for that to have a solution, so kind of walk through our system of linear algebraic equations, diagnostics, for that to have a solution, it has to be singular. A minus lambda I must be singular. So let me walk us through that. So if A minus lambda I was such that its determinant was not equal to 0, so it's not singular, then we could take the inverse of this A minus lambda I matrix, multiply it on both sides of the equation, and I would have U is equal to the inverse of A minus lambda I here times 0. Well, what's the inverse times 0? Of course, it's 0. So that would just give us U is equal to 0. So that would be the trivial solution, which we don't want. So in order for us to get a non-trivial solution, the only way that could happen is if the coefficient matrix is singular, such that its determinant is equal to 0. And you notice now this is not bold, this is a scalar 0 because it's the determinant of this A minus lambda I. If that is equal to 0, then the coefficient matrix A minus lambda I is now singular. And because of its homogeneous system, that's the only way that we could get a non-trivial solution. I know that's a little confusing. It's the opposite of what we normally want. What we normally want is the determinant not to be equal to 0, so that we can get an inverse, and then we can get a unique solution. U is inverse of A times B. But in this case, because B is 0, we actually want a non-trivial solution. And the only way that we can get a non-trivial solution is if, excuse me, the system is actually singular. The A minus lambda I is actually singular. So just think that through. The logic is a little strange at first, but that's the logic. All right, so if I write this out, A minus lambda I, it looks like this. So I have my A matrix here, and I just subtract off lambda off of the main diagonal elements. So that's from here, minus lambda times I, as always, is just ones down the main diagonal, zeros everywhere else. And so this is predominantly just the original A matrix, but I'm subtracting off lambda off of the main diagonal terms. Then I take the determinant of that and set it equal to 0. And then I want to find the lambdas, the values of lambda, for which that is true. Now, when you take the determinant of a matrix like this, you'll get what's called the characteristic equation. The characteristic equation will be a polynomial, and it'll be a polynomial of degree n. So if n is 2, so if this is a 2 by 2 matrix, then we'll get a quadratic equation. So it'll be something times lambda squared plus something times lambda plus something is equal to 0. If it's 15th order, so n is 15, then we'll get a degree 15 polynomial with lambda to the 15, lambda to the 14, 13, and so forth all the way down. Now, obviously, other than quadratics or maybe cubics are hard to solve by hand. So we'll often need software to do this, and we'll talk about that in chapter 5, how we actually get the roots or solutions of any kind of equation, not just these characteristic equations, but any kind of nonlinear equation. All right, but the point is, those are the eigenvalues, the solutions, the roots of our characteristic equation, the values of lambda that satisfy the characteristic equation, of which there will be n of them. Those are the eigenvalues. So we start with A, we form A minus lambda I, take the determinant, set it equal to 0. That gives us the characteristic equation, and we solve the characteristic equation for the values of lambda that satisfy that. And those are the eigenvalues. So that's the basic structure. Those are the basic steps. Now, for each lambda, then, you're going to get an eigenvector. So I have capital N eigenvalues. We'll have capital N corresponding eigenvectors, one for each. So lambda 1, U1, lambda 2, U2. So we'll have an eigenvalue, eigenvector in pairs. So just as a simple example, if n is equal to 3, so we have a 3 by 3 matrix A, then the characteristic equation is going to look something like this. It's going to be a constant times lambda cubed plus a constant times lambda squared plus a constant times lambda plus a constant is equal to 0. So a third order polynomial for lambda. When you solve that, you'll get 3 values of lambda, lambda 1, lambda 2, lambda 3, and then those will correspond to the eigenvectors U1, U2, and U3. Now, as you might guess from a course like this, these can be obtained very straightforwardly using MATLAB, using Python, using mathematical software. So that's, of course, what we will be doing. We just want to understand the mechanics, what they mean, how they come up physically, which we'll look at in a second. Okay, first of all, any questions about that or anything from last week's lecture, which was posted on Blackboard? Obviously, we didn't get a chance to talk about those topics, the iterative methods. So any questions about iterative methods or anything about this so far? Okay, so let's talk about the first physical example, principal stresses that I introduced before. So again, this comes from 202, MMAE 202, or 313 in a fluid mechanics context. So the idea is as follows: if you take an object, we'll talk about a solid object, but it could be a fluid. You take an object and you put external forces on it. That's going to induce a stress distribution throughout the interior of that object. at every point in the object, you'll have a series of stresses acting in different directions, multiple directions. So the way we represent that is as this small, infinitesimally small tetrahedron that you see here. So this is a blown up, tiny little infinitesimally small piece of the solid that's been blown up so that we can see it. And what we want to see are the stresses that act on each face of the object, the tetrahedron. And we want to be able to calculate the static equilibrium of this. And what we'll see is when we ask the question, well, let me describe these first, then I'll ask the question. So on each face, we have three stresses. There's a normal stress, normal means perpendicular. So there's a normal stress, sigma x, sigma y, and sigma z. So those are normal stresses perpendicular to the three surfaces, these three orthogonal surfaces here. Then we also have on each face two shear stresses. So we have a normal stress, normal, perpendicular to the plane, and we have two shear stresses, one in each of the directions of that plane. So let's take this face right here in the back. So that face is in the y, z plane, and x is perpendicular to that plane. So sigma x gives the perpendicular direction. That is the normal stress. It's in the x direction. Then the tau's are the shear stresses, and you'll notice they have two subscripts. The first subscript tells you the face that they are on, and the face is determined or defined by the outward facing normal. So this is an x face. It's in the YZ plane, but the outward facing normal is in x. So this is the x face. So that's why the first subscript is x for all three of them. Then the second subscript gives you the direction that the stress is acting. So this one, for example, tau xy, it's on the x face, and the stress is in the y direction. It's in the y direction. Same thing here. This is the xz stress, tau xz. So the stress is on the x face, but acting in the z direction. Now, the reason why these are all minus, so minus x, minus y, and minus z, because the face is in the back. If it was in the front, they'd be pointing in the positive x, y, and z direction. That they're in the back, so they point in negative. That's a detail we don't need to worry about. Then the same thing is happening on this face, which is the y face. That's this one. And then this face, which is the xy face. All right, so that's how the notation works. Now, what we want to do is we want to ask the question. So this is a particular point inside our solid. And what we want to know is, how can we determine an orientation of that little infinitesimal piece such that we only have normal stresses? We don't have shear stresses. Now, of course, the first question is, how do we know that that's even true? And physically, it's actually quite hard to justify that or prove that that has to be true. Mathematically, it is, because of the eigenvector and eigenvalue relationship that we're going to see in a moment. So we'll kind of hold off on that. But if you just take my word for it for now, there is some orientation, a special orientation, with respect to which, when it's in that orientation, there's only normal stresses and no shear stresses. And that's what we want to determine. We want to determine what that orientation is, and we want to determine what those stresses are. So when I ask that physical question, that's a straightforward physical question that we want to know, and then I want to determine how we answer that question. And as you'll see, the answer to that question, that physical question, is mathematically a question of determining the eigenvalues and eigenvectors of what's called the stress tensor. So this face, this BCD face, that has an area A, and it has a force in the normal direction to that face. It's on an oblique angle. That's sigma. And so the stresses then make up the stress tensor. It's a 3x3 matrix. Whenever you hear the word tensor, remember there's scalars, vectors, and matrices or tensors. A tensor is just a 3x3 matrix. It's just a special matrix that has some sort of physical meaning to it. It's not just a generic matrix, it has a specific meaning to it. So we denote it by tau, and it's a bold tau because it's a matrix. It's 3x3, and it has the normal stresses down the main diagonal, sigma x, sigma y, and sigma z. So in some notations, people say tau xx, tau yy, tau zz. It's because they're on the x, y, and z face respectively, and they're acting in the x, y, and z directions respectively. So a lot of people use sigma x, y, z. Some people use tau xx, tau yy, tau zz. They're synonymous. So those are the normal stresses on the main diagonal. On the off diagonal are the shear stresses. So these are the tau xy's, tau xz's, tau yz's. Now you notice here I have a tau xy, here I have a tau xy as well. Those are the same. So the the stress tensor is symmetric. And that's based on physical considerations. If it wasn't symmetric, then this thing would actually be spinning around. It would not be in static equilibrium. You'll learn about all those details in 202 if you haven't had that already. So it is a symmetric matrix. Not all tensors are symmetric, but many of them are. And so there's actually, rather than 9 unique values that make up the tensor, there's actually only 6. 1, 2, 3, 4, 5, 6 because of the symmetry. Anyway, those are not very necessary details at this stage. So we have the sigmas, those are the normal stresses. We have the taus, those are the shear stresses. So it's just a nice, very organized way to compile all the stresses, normal and shear, into a nice, neat tabular form, in this case, in a tensor. Now, this is a 3x3 matrix. As we just discussed, all 3x3 matrices have the property that they have 3 eigenvalues and 3 eigenvectors. And the question is, in a physical context such as the stress tensor, what do those eigenvalues and eigenvectors represent? What do they physically represent? Turns out that the principal axes, so those are directions, the principal axes are the coordinate axes with respect to which we only have normal stresses, no shear stresses. Okay, the principal stresses are the eigenvalues. It's those normal stresses. It's the value of the normal stresses. So this is where the physics and the mathematics gets coupled together in such a way that we can learn something about the physics from the mathematics, and it helps us better understand the mathematics as we look at the physics as well. All right, so we want to formulate this. Again, we're asking a specific physical question. For a given stress distribution, what orientation of my little infinitesimal element has this property that there's only normal stresses acting and no shear stresses? So what are the principal axes, in other words, and therefore what are the principal stresses as well? Okay, so to derive this, and the details of this are not important. I'm going to go through them. All the details are here. I'm not going to skip over any steps, but this is not the important aspect of this. I'm never going to ask you on this on an exam or even on a homework problem. So I will go through the details so you can see where this comes from. So we have the normal stress, the normal unit vector that's on the the BCD face. Okay, so we have a normal vector from that oblique face. It has that face that has area A. All right, so the normal vector we can write in XYZ coordinates as NXI plus NYJ plus NZK. So I, J and K have their usual meaning. Those are unit vectors, vectors of length 1, acting in the X, Y, and Z directions respectively. And then NX, NY, and NZ, those are scalars. Those are the magnitudes or the components of N, which is a vector, acting in the X, Y, and Z directions. All right, so that's just a vector that defines or describes that normal vector to the BCD face. Now, static equilibrium, this object is not moving. This little infinitesimal element is not moving, it is static. So we can apply the principles of statics, which just tells us if we take the sum of the forces in any direction, they should be equal to 0. So let's just do that. Again, don't get bogged down in the details of this. They're all here and they're correct, but this is, I'm not going to ask you to recreate this. I just want you to see how this leads to an Eigen problem in the end. So if I take the sum of the forces in the X direction, a force is a stress times an area. So on that oblique face, which has area A, the component of the force, well, the stress, the force is the stress times the area. The component of the stress in the X direction will be sigma n times the normal vector n dotted with I. Remember, when you take the dot product of a vector with a unit vector, it gives you the component of how much of that vector goes in that direction. So in this case, the X direction, the I direction. So how much of sigma n goes in the X direction, that's what this gives us represented here in parentheses. Again, multiply by the area, that gives us the force. Then we have all of the other stresses that are acting on the other three faces. So I have a stress sigma x acting on the X face times the area times n dot I. So that's the component of the area projected in the X direction, in the Y direction, in the Z direction, and the corresponding stresses. So tau xy times its area, tau xz times its projected area. So that is simply just adding up the forces in the X direction and setting them equal to 0. We're simply enforcing static equilibrium, a physical principle. So when I simplify this, the A's all cancel, because I have an A in every term, so those all cancel. When I take these dot products, I get components of n. So on the left, I have sigma n nx. Nx is n dotted with I. Just like here, n dotted with I, so that's nx. N dotted with j, ny. N dotted with k, nz. So we have the sigma acting on the oblique face times its component, sigma x acting on the x component, x tau xy on the y component, tau xz on the z component. So again, it's just stress times area giving us force, adding up the forces, summing them to 0. Do the same thing in the y and z direction, and you get similar equations. And again, the details aren't terribly important. If you're interested, fine. You'll do this in 202. So I just want you to see that connection, but the details aren't terribly important to us. So now I have 3 equations for 3 unknowns. The unknowns are the nx, ny, and z. It's that face, the BCD face, on which I only have a normal stress. That's what I'm looking for. So if I put it in matrix form, guess what I have? I have my stress tensor here, just like we had before, so that's tau. I have the n vector. I have the n vector again on the right-hand side, and then I have this constant sigma n times that. This is an Eigen problem. A matrix A times a vector u, or in this case n, is equal to lambda, in this case sigma, times u, which again in this case is n. So again, I asked a physical question what is the orientation of a face that I only have normal stresses on, no shear stresses? And then the mathematical answer to that question is, oh, well, you need to solve an Eigen problem. And the the eigenvalues will give you the values of sigma. So those are the principal stresses themselves, the normal stresses. And then the eigenvectors, oh, well, those are going to be the principal axes, the directions that those stresses act, those principal stresses act. So mathematical question has a physical question has a mathematical answer. And in this case, that mathematical answer is find the eigenvalues and eigenvectors. So we'll do an example of that in a moment. Principal moments of inertia, same idea. So there's a 3x3 moment of inertia tensor. It has all the moments of inertia of a three-dimensional body in them. And it's also symmetric. And then you can, because it's a 3x3 matrix, you can find an orientation of this object such that you only have normal moments of inertia, or moments of inertia. You don't have any products of inertia. So you only have Ixx, Iyy, Izz, no Ixy, Ixz, or Iyz. Once again, the eigenvectors correspond to the coordinate directions on which those principal moments of inertia act. And then the eigenvalues correspond to those moments of inertia. So once again, physical question, mathematical answer is an Eigen problem. Okay, the other physical scenario that I want to highlight is natural frequencies, which we discussed a moment ago. So let's look at a simple spring mass dynamical system. So again, this is something that you might see in MMAE 305, for example, or even a physics class. This is an easy dynamical system. So we have two masses, a mass m and a mass 2m. They are connected by three springs. One has spring constant 2k, the other two have spring constant k. The position of the left mass is given by x1. The position of the right mass is given by x2. Now these are such that when everything is in its neutral position, so the left mass is at x1 is equal to 0, the right mass is at x2 is equal to 0, this is such that there's no forces in any of the springs. Everything is nice equilibrium and there's no forces anywhere, nothing happens. And so the question is, we want to be able to, for example, if I take this mass and I pull it to the right some distance, and then I let it go. And then, so this spring mass system is going to wibble wobble back and forth, left and right. Both of the masses will be oscillating back and forth. And we want to know, how does that happen? What are the governing equations of that process? More specifically, I want to look at the natural frequencies of vibration, which I'll discuss what those represent in a moment. Whenever we're dealing with dynamical systems, the first thing we ask ourselves is how many degrees of freedom the system is. And the easiest way to answer that question is just to ask yourself, what's the smallest number of dependent variables that I would need to know, that I would have to be able to specify in order to determine all there is to know about the system? So in this case, it's 2. If I know x1 and I know x2, then I know where these two masses are. If I know where these two masses are, I know the elongation of these three springs. I know the forces in those springs, and I can calculate anything I want about this system if I know x1 and x2. So it's a 2 degree of freedom system. And what that means physically is there are 2 natural frequencies. So there are 2 tones at which the opera singer can sing that will cause that glass to shatter if it has 2 natural frequencies. Then the general motion for any initial conditions, any situation that you can think of where this system is wibbly wobbly back and forth, is a superposition or a combination of those 2 modes, those 2 frequencies. So we can get the natural frequencies, that's what we'll do in a second, and then those tell us something about the system itself. And in addition, those give us an indication of, in this case, the 2 frequencies that when combined, some amount of the first frequency, some amount of the second frequency captures the full motion of the dynamical systems as it wibbly wobblies back and forth. Okay, so let's do it. So put your MMAE 305 hat on. You want to get the equations of motion of our spring mass system. So we use Newton's second law, which is F equals ma, force is mass times acceleration. Remember, acceleration is the time derivative of the velocity, and the velocity is the time derivative of the position. So the acceleration A is just x double dot, where x is position. So the second derivative in time of the position is the acceleration. So F is equal to mass times x double dot. Great. We apply that to free body diagrams. So we take a free body diagram for the left mass, it'll be up here, and then we'll do the same thing free body diagram for the right mass, mass 2. So the left mass is mass 1. The spring on its left is pulling with the force 2k times x1, so the spring constant times the elongation. And again, we're not in 305, so don't get too excited about, well, what is it positive? Is it negative? Should I put the arrow to the left? Should I put the arrow to the right? Don't worry about those details. Just again, follow along the major steps and the overall picture. The right spring, which is the spring between the two masses, its force will be spring constant k times its elongation, which is x2 minus x1. It's the distance or the difference between those two x's. That's the elongation of that middle spring. So mass times acceleration, mass times d squared x1 dt squared, or x1 double dot, is equal to the sum of the forces. So k times x2 minus x1, and then my arrows to the left, so minus 2k x1. And I can simplify that a bit to minus 3k x1 plus k x2. Okay, so that's the governing equation of motion for the left mass. And you can see it involves both the position of the left mass and the right mass. We need to know both of those in order to solve the left mass. It's a coupled system. What happens to mass 1 and mass 2 are interrelated. Do the same thing for free body diagram for the right mass, which is 2m. The force pulling to the left is the same as this one pulling to the right. That's k times x2 minus x1. And then this force, I showed it pointing to the right, but it's negative, because if it's to the right, that means it's in compression. Again, don't get bent out of shape. Don't worry about the science. I just want you to see where all these details lead to. So that's minus kx2. Again, spring constant times elongation. Mass, which is 2m, times acceleration, which is x2 double dot, is equal to the sum of the forces minus kx2. This was to the left, so minus k times x2 minus x1 simplifies to kx1 minus 2kx2. So we have two equations of motion corresponding to our 2 degrees of freedom. They are coupled together. I can't just solve one for x1 and the other one for x2. I have to solve both of them simultaneously together because they both involve x1 and x2. So they're coupled, and they are second order. The highest derivative is 2, so we say that they are second order. So we have 2 second order ODEs for my 2 degrees of freedom, and that's typical of dynamical systems governed by Newton's second law. All right, what I want to do is find the natural frequencies of this system. Now we could solve it, and we will do that later in the semester. So when we solve differential equations, we'll get the solutions to those governing equations of motion later in the semester. But for now, I just have a simple question. It's a physical question. What are the natural frequencies of my system? So a natural frequency in this case is I have 2 masses and 3 springs connecting them. The natural frequencies are when the masses are moving with the same frequency. Both masses have the same frequency. They could be out of phase, so they could be going together left to right, or they could be going opposite directions, but they have the same frequency. They might have different amplitudes, so one is moving with a small amplitude, one has a larger amplitude, but the point is they're moving with the same frequency. We also call these normal modes. So because of that definition, I can say, okay, fine. I know that x1 is going to have some amplitude, call it a1, times cosine of omega t. Omega is a natural frequency. It's moving with some natural frequency omega. x2 could have a different amplitude, but it has the same frequency. So they're both moving. A1, A2 could be negative, so again, not necessarily the same direction, but they're both moving with the same frequency. Now, again, that's not normally the case for most motions of the system, general motions of the system. What we're trying to do is ask, again, a physical question. What would have to be true for this to vibrate with the same frequency, both masses with the same frequency? I actually don't care about the A amplitudes, A1 and A2, but you'll see what happens with them in a moment. What I care about are the natural frequencies, the omegas. Now, this is one way to do it. So I hardwire in that my motion is going to be like a cosine omega t, cosine omega t. Another way to do it is use exponentials. So e to the I omega t, e to the I omega t, where again, omega is the natural frequency that I'm looking for. Either way is fine. Mathematically, they're both correct. The advantage of doing it this way is if I have first order derivatives as well. I don't in this example, but if I had first order derivatives, then I would use this way to take care of that. Because the problem with cosine is if I use sine or cosine, if I take the derivative of cosine, I get a sine. So now I have a cosine in some terms, a sine in some other terms. If I take a second derivative, cosine, first derivative of cosine becomes a minus sine, and the second derivative of sine becomes, well, second derivative of cosine is first derivative of sine, is equal to, I've got myself so confused, it's back to a cosine. So then all the terms, if it's only second order, all the terms have cosines in them. So in any case, you can use either approach. This way works fine here, or this way works fine here. We'll do it this way. And so if I take the second derivative of x1 with respect to time, again, my cosine becomes a minus sine, and then the sine becomes a cosine. So I have minus cosine a1. Every time I differentiate cosine omega t, it spits out an omega. So I differentiate twice, so I get two omegas. So I have minus a1 omega squared cosine omega t. And you'll notice it has the same frequency, cosine omega t. Same thing with x2 double dot, will be minus a2 omega squared cosine omega t. So I substitute these two expressions in for x1 double dot, x2 double dot on the left-hand sides of my two governing equations. And look what happens. On the right-hand side as well, I'll substitute in x1 and x2. And look what happens. So when I do that, I get this. And the reason why there's no cosines left is because every term has a cosine omega t in it. So I can just lop those off. I can cancel all the cosine omega t terms, and then I get my first equation results in this algebraic equation, and my second differential equation results in this algebraic equation. And you look at that and say, well, I don't know what that means. Well, let's rearrange it a bit and make it a little bit more obvious. I'm going to combine the m, the k, and the omega together. So you see an m omega squared here, and then k is over here. So I'm going to bring the k over to the left-hand side, and m omega squared over k, I'm going to call that, I don't know, let's just pick some random Greek letter. Let's pick lambda. So lambda is m over k omega squared. So with that, and I'm going to switch the sides of the equation, make it even more obvious. So with that, the left-hand side here, these two, become 3a1 minus a2 and minus a half a1 plus a2. But look at the right-hand sides. They're lambda a1 and lambda a2. So in matrix form, I have a 2 by 2 coefficient matrix, 3 minus 1 minus a half 1, 3 minus 1 minus a half 1, times a1, a2, those are the amplitudes, are equal to lambda times a1, a2. So asking the physical question, what are the natural frequencies of vibration of this spring mass system, results in having to ask and answer the mathematical question, what are the eigenvalues and eigenvectors of this 2 by 2 matrix? And that's it. It's that simple. So if I can find the eigenvalues and eigenvectors of this 2 by 2 matrix, those give me the eigenvalues, lambda, which are related to the natural frequencies. And then the A's actually are the eigenvectors. I don't care about the amplitude, so I don't really care about the eigenvectors in this case. But again, the eigenvectors do have a physical meaning. And then once I have these, I know that the general motion of the system is the superposition or the combination of these two natural frequencies. So no matter what I do to the system, it's just going to be sum of mode 1 plus sum of mode 2, wibbly wobbly vibrating back and forth. And that's how the physics and the mathematics goes together. Okay, any questions so far? And I'll solve this in a second. We'll find the natural frequencies next. But any questions before I do that? All right, so we have AU is equal to lambda U. I multiply by I on the right-hand side. I bring that over to the left, and I have A minus lambda I times U is equal to the 0 vector. For that to be true, the determinant of the coefficient matrix A minus lambda I has to be 0. Here is that expressed and written out in the 2x2 form. So the determinant of a 2x2 matrix is 3 minus lambda times 1 minus lambda. You see that here. Minus 1 times minus a half. You see that here is equal to 0. So you multiply that out and you get this quadratic equation. Lambda squared plus 4 lambda plus 2.5 is equal to 0. It's a quadratic, so we can solve it using the quadratic formula, minus b plus or minus square root of b squared minus 4ac over 2a, which is this. And when you simplify that down, it becomes 2 plus or minus root 6 over 2. Again, how many natural frequencies are there? There are 2, because there's 2 natural modes of vibration or natural frequencies of vibration of the system. And all of that is consistent with the fact that it's a 2x2 matrix with a second order characteristic equation. Okay, so now remember the frequencies, omega, are related to the lambdas in this way. So I can solve for the omegas, and again, there's 2 of them. They are going to be the square root of k times lambda over m. So let me just keep the square root of k over m over here. So whatever the k is, whatever the m is, again, those are spring constants and masses. Then I have the square root of 2 plus or minus square root of 6 over 2 out front. Now those numbers, if you get the numerical values of these, if it's positive or negative, you get 0.8805 and 1.7958. So those are the 2 natural frequencies for a given k, spring constant, for a given mass m. Then you can evaluate these and get the 2 plus and minus, so you get the 2 natural frequencies of vibration corresponding to the 2 modes, omega 1 and omega 2, corresponding to the 2 modes, the 2 natural frequencies. Now the smallest one, this one, is called the fundamental mode. And in some applications, it's not terribly important here, but in some applications, it's the lowest one that you care about because that's the one you're going to hit first. Like in a stability context, you'll have a whole bunch of frequencies that are unstable. It's oftentimes the lowest frequency that's the one that you would hit first, and that's the one you care about. Another example of that is buckling. Buckling is also an Eigen problem. It's the lowest mode, the fundamental mode of buckling. That is the one that gets hit first, the smallest load that will cause a column or a beam to buckle. All right, so in any case, we will look at the solution of the full equations later on, towards the end of the semester. And what we'll see is they will be linear combinations, so some combination of these 2 frequencies, some of omega 1 and some of omega 2. But again, for now, I just want you to see that if I ask the physical question, what are the natural frequencies of vibration of this spring mass system, that ends up being mathematically answered by, oh, well, what are the eigenvalues of this Eigen problem? And here they are. Okay, some comments about this. This is an important one. So if you notice how this equation is expressed, if I multiply u by some scalar, that scalar just cancels out. And so what that means mathematically is my eigenvectors can be multiplied by any scalar. So you will often see them expressed a little bit differently. In other words, if you look at, if if I asked 2 of you or 10 of you to get the eigenvalues and eigenvectors of a system, oftentimes your eigenvectors will look a little bit different. And the reason is because you'll make different choices about what the constant is that's multiplying these u's. So just as an example, I could have an eigenvector that's 1 minus 1. That's actually the same as minus 1, 1, because if I multiply this first one by minus 1, so minus 1 on both sides, that still satisfies my Eigen problem. So that's still the same eigenvector. Or maybe 2 minus 2, or 3.497 minus 3.497. So there's an infinity of eigenvectors that correspond to the same eigenvalue. That gets confusing because I said there's only one. So we really think of it as all of these are the same eigenvector. So technically the correct way to write this would be U, like in this case, you would say U1 is equal to C times 1 minus 1. And that is explicitly expressing the fact I can choose any C and this is still the same eigenvector. So here it's C is minus 1, here it's C is 2, here it's C is 3.497. So if you look at someone else's solution, if you look at my solution, I might have different eigenvectors than you do. It's the same thing for mathematical software. So if you ask MATLAB or Python to get the eigenvectors of a matrix A and you put the A into MATLAB, you put it into Python, you put it in Mathematica, it might actually give you different eigenvectors. They might be in a different order, or maybe one gives you 1 minus 1, whereas the other one gives you minus 1, 1. So I just want you to be aware of that. And it actually makes sense. It's reflecting the fact that the solution of a singular system is not unique. Remember, that was the whole basis for the Eigen problem, is I want a non-trivial solution. The only way to get a non-trivial solution of a homogeneous system where B is 0 is if it's a singular system. If it's singular, that means it doesn't have a unique solution. So it actually makes sense that there's an infinity of possible solutions. Having said all that, we consider this, or this, or this, or this, or whatever. We consider that to be the eigenvector. In other words, a lot of times we don't include the C. We just say the eigenvector is 1 minus 1. The C is implied. It's always there, and we're just lazy not to write it all the time. Now, how do we get these for very large systems, very large matrices? We use a method based on what's called QR decomposition. That's not something we're going to talk about in this class. It's a more advanced linear algebra technique. But if you're interested in that, when my book finally does come out, it's in section 6.5. So for ones we do by hand, they need to be small so we can factor the characteristic equation to get the lambdas. But just know that for large systems, there is a numerical technique, and it's based on this QR decomposition. And that's actually what all of these different systems use. So MATLAB, Mathematica Python all use QR decomposition to get the eigenvalues and eigenvectors of a large matrix. It can be shown to be quite efficient, and it's relatively straightforward to do on any size system. Well, within what can fit in your computer. Now, how you get these in MATLAB, there's an Eig command. So if you just say Eig of A, and if you just put an L on the left-hand side or whatever you want to put, that is a 1D array or a vector that it's going to return. And that vector has the values of the eigenvalues in them. So if A is n by n, you'll get an n by 1 vector back that includes the n eigenvalues. Now, the same Eig of A command or function can also give you the eigenvectors. So if you say Q comma L is equal to Eig rather than just little l, then you'll get two matrices. The L matrix is going to be a diagonal matrix with the eigenvalues along the main diagonal. So notice, instead of giving you L as a vector with the eigenvalues, it gives you the eigenvalues along the main diagonal of a diagonal matrix, which is kind of strange, actually, especially if these are very, very large. It's kind of a strange way to express it. But anyway, that's the way MATLAB does it. So L gives you the eigenvalues along the main diagonal of a diagonal matrix. And the Q matrix is going to be a matrix that has its columns are the eigenvectors. So the first column of Q1, the first column of Q is U1. The second column of Q is U2. Third column of Q is U3, and so forth. We'll skip over Mathematica. Python, you use the SciPy linalg package. So linalg eigenvals of A will return a vector or a 1D array that contains the eigenvalues, just like in MATLAB. Or there's a linalg eig of A command function, and that returns the vector of eigenvalues and the matrix of eigenvectors. So you can see a little bit of a difference here. So now it's not returning like MATLAB a matrix with the eigenvalues along the diagonal. It's still just giving you, just like the eigenvals function, it's still just giving you a vector of the eigenvalues, which actually makes more sense. And then it gives you the Q matrix, which has the eigenvectors in it. The difference is the eigenvectors are actually the rows. So the first row of Q is the first eigenvector. Second row of Q is the second eigenvector. So you need to be very careful and take special notice of whatever system you're using, whether it's MATLAB or Mathematica. Do the eigenvectors come back in the columns or the rows of Q? And it doesn't matter mathematically, but you need to know. So if I'm going to extract out U1 or U2 or U3, I need to know, am I taking the first column or the first row? Why we can't all agree to just do the same thing, it's kind of annoying, but that's just the way it is. Okay, this is actually problem set 2 here. So problem set 2 is on Blackboard. I told you last week, in class last week, that you could do most of problem set 2, and now you can do the rest of problem set 2. I think it's the last 2 problems are based on eigenvalue, eigenvector problems. Oh, words of wisdom. So this is true generally of these words of wisdom. These are not just for this class. They apply to this class, but I'm generally stating them more generally, so they apply to all of your classes. Now, this one is one that you've been told many times. You've been told this in physics classes in high school and your early years in college. You've been told this in other classes like thermodynamics and 200. And a lot of you ignore these recommendations because when you're doing simple problems, they don't seem terribly important. The problem is when we tell you these don't seem necessary, then when they are necessary and extremely helpful, you've developed bad habits already and you don't do them. So I'm going to remind you, and maybe just one of you changes your ways and improves on how you formulate your problems, then I will feel like I've accomplished my goal for the day. So I want to emphasize how important it is to have an orderly solution procedure. I won't embarrass myself and show you my solution procedure the way I did it in college. You will probably laugh at it because it tends to use a lot more paper than is necessary. In fact, once I became a professor, I always became amused at how many students seem to have as their objective to complete an entire homework assignment on one sheet of paper, and some even on one side of one sheet of paper. I take many pages because I have a lot of white space, I skip lines, I have things that don't seem necessary, but I think they're very helpful. I would always write out the problem statement for reasons I'll mention in a second. So this is very important, and if you can develop good habits along the way, it will actually benefit you. And that's part of my argument here, is I want to argue why or how this benefits you, not just me or someone else. So an orderly solution procedure: do problems in a neat and organized fashion, draw a neat and clearly labeled schematic. How many times have you heard that? And again, when you were first told to do this, usually the schematics were really trivial. They were really simple. And you thought, well, what's the point? I'm just drawing an arrow in the, in the east direction. And so you develop the bad habit of not doing it. Include coordinate systems. Again, simple problems, the coordinate system is so obvious that you think, well, why bother taking the space and the time and the ink or lead to actually show it, to draw the picture? Get out your little ruler and draw a nice picture of a schematic of the system along with the coordinate system. The problem is, as the problems get more complicated, especially as you get into dynamics and so forth, now what is the coordinate system makes all the difference in the world. If you choose one coordinate system and someone else chooses another, you're going to get different equations of motion. And it's not always obvious what the coordinate system should be. And so you may make a different choice than I do, and that's perfectly fine. It's not that one is right and one is wrong, or even that one is better than another. So you need to be very clear in how you make a schematic of the problem itself, include the coordinate system. And the reason why this is so important is it helps to organize your thinking. It literally orientates your thinking. You get oriented to think, okay, so my spring mass system, movement to the right is positive, movement to the left is negative. So you have an orientation in your mind that's completely arbitrary. There's no reason why it couldn't be the opposite, but you have in your mind what the orientations mean. It clarifies your solution approach. So in the spring mass example, the details of what the sign should be, well, that's confusing. You need to make sure you get that right. Otherwise, you'll get the wrong equation and you'll get the wrong answer. So it'll help clarify the solution approach and as well as the details of the solution. It also assists you in interpreting your results. Whenever you're doing physical problems, especially physical problems, at the end, don't just be happy to get some number. Stop and think, does this number make sense and what does it mean? So it means the member of my truss is in compression. It means it's in tension. Does that make sense physically? Is that intuitively consistent with what I think is going on? And so asking questions like that, and so, or interpreting the results. So I got a negative number, that means it's in compression. Okay, that's useful information. You're also more likely to get the correct answer. And I can't tell you how many times, and of course you guys will argue with me, but I can't tell you how many times that this is the case. So just following a neat and organized procedure, even though it may take a little bit more time, and also maybe takes a little bit more paper, it will be more likely that you'll get the correct answer. Not only that, even if you get the wrong answer, you'll often get more partial credit, not because we're grading you on neatness and organization, but because we can follow your thinking more clearly and we can see what's right and where you've gone wrong. And so it's very often the case that a nice, neat, well-organized solution, I can see more clearly what you're trying to do, and I can see where you've gone wrong, and I can give you more partial credit based on that. This is one that is very much underappreciated. And this is what always motivated me. Why would I write out the problem statement? Well, for one, it made sure I was clear on what the problem was asking for. Sometimes you read a problem statement and you get in your mind what it's asking for, and that's not consistent with what it's actually saying. So writing it out would make it clear what it's actually asking for. But also, when I went back and studied, all I needed was my solutions. I had the problem statement, I had whatever assumptions I was making, I had a nice schematic of the problem itself, I had a clear definition of the coordinate system, and then step-by-step process to get the solution and interpretation. So everything was in one place. I didn't have to look back at the book. What was the problem that I was trying to solve in this little 1-inch, sliver of my page? So the neater you are, the more organized you are, the more helpful and useful your homeworks are and the problems are that you do for studying. So I just encourage you to kind of rethink how you do those sorts of things, how you do your problems, and try to kind of nudge yourself into developing good habits and good practices, and maybe shedding some of the not so good practices. All right, curve fitting and interpolation. We only have 5 minutes left of class, so I'm not going to start this. I'll just say a little bit about it, and then we'll see if you have any questions. You guys have been very quiet today, which is fine, but it just makes me sad. So I don't like teaching to my computer. This is not enjoyable. I like seeing faces, human faces, and having a little bit of human contact. So this is kind of not natural for me. Talk about natural frequencies. And I tend to get a little loopy. And anyway, so curve fitting is a very useful, very powerful topic. It's something we'll come at from various different angles. And basically, it comes from the fact that so many of our systems as engineers are just going to provide data. We're just going to get numbers out of these systems. We have to make some sense of those numbers. What do the numbers mean? What do the numbers represent? How can we represent this set of data in some functional form? Does it look like a straight line? Does it look like a quadratic? Does it look like an exponential? What does it look like? And can we fit such a curve to that data? So we're going to address that. And we'll look at some fun examples along the way. There's a really interesting example using sunspots. And the thing about this is the data goes back for several hundred years. We have data going back several hundred years on people counting the number of sunspots every year. And so we can use this data to learn some interesting things about the sun's behavior. We'll look at some image data and we'll process some images and see how that can be done using these techniques and what kind of information we can get out of that. So we'll start walking through that on Thursday. So in the meantime, are there any questions before we adjourn? So again, I'm assuming, I don't think there's any reason to think that we won't be back in person on Thursday. So I'm looking forward to that. I hope to see some smiling faces hidden behind masks on Thursday. But in any case, so problem set 1, you turned in, you can now complete problem set due. It's due midnight on Friday. And the TA, I believe, has been grading problem set 1. So I don't know if he's done yet with those or not, but those you should be able to see on Blackboard soon, if not already. All right, so I will see you on Thursday. And again, enjoy the snow.